All right, let's get started here. Okay, guys. All right, so we're going to see if this works. I believe what I've done, started Zoom, started sharing my screen, so it should be capturing the screen. It should be picking up the audio. I'll see what happens. It's recording, so we'll see. If anybody saw something that looks like it wasn't going to work, now would be the time to say that. Okay, so where were we last time? We did a very slow walk through Gaussian elimination. And when we were doing that, we kept careful track of the row operations in a very detailed way, allowing us to then find elementary matrices to encapsulate each row operation. We then combined the elementary matrices such that we got matrices we labeled M1 and M2, which captured all of the row operations to make zeros below a pivot position. We went through this whole procedure, and by doing this, we were able to factor a matrix A into L and U, where L was lower triangular and U is upper triangular. And we had a very good question at the end here from the front, which is, why are we doing this? And we sort of answered that a little bit, but we're just going to say a little bit more about that. So why form the LU decomposition? One reason is repeated linear solves. So that means you're like this, AX equals B, and you have many different B. This is actually not that far-fetched. It's not just a far-fetched idea, because what you might have is you have a linear system where your coefficients on your equations is capturing something about your physical situation, and then you measure something and you want to solve for that measurement. Your measurement being B. Then you measure something else and you want to solve for that B, and you measure something else. So it's actually not that uncommon for this to happen. For example, your matrix A could be capturing the parameters of your MRI machine. And then the B is when you go in the MRI machine and get measured. And then you want to find out, you're solving for basically X to see what's going on, okay? So this is a practical situation. So you want to do multiple solves with the same A, but different Bs. Okay. The normal thing is if we were to do it repeatedly by Gaussian elimination without factoring. So let's just put this down to solve each system with Gaussian elimination. That is approximately, well, this is a single one, 2/3 n cubed. I recognize that we had a small hitch with this. I haven't written out the correction to that yet. That is on my list of things to do. That would be per time. So imagine that we want to solve, we have many different B's. Let's just say K of them. So we want to do this operation, AX equals B in this way, AX equals B1, then we want to do AX equals B2, etc. So we want to do this, and we're going to do it K times. We're going to sort of see what the amount of time is looking like here. So if we were just going to form a new augmented matrix every time and do it over and over and over again, we would end up doing 2/3 n cubed, and we would do it K times. So that is possibility one. Possibility two is that we do we factor A equals LU. That's going to take That is Gaussian elimination. That is going to take 2/3 n cubed of flops. And then we're in the situation at that point where we have ax equals to b. And now because we've done the factorization, that is equivalent as LU, that is A, factored as LU, x is equal to B. Then what we do in this case is we solve group these two together like that. We're going to group those two together. We're going to call that y. So we're going to solve Ly equals B by forward substitution. It's an upper triangular, it's a lower triangular matrix by forward substitution. It's triangular by forward substitution. And then after that, we're going to solve ux equals to y. Y is ux. We actually want x. And we're going to be able to solve that because u is upper triangular by backward substitution. Okay. So forward and backward substitution is n squared operation. So what we end up having happen here is we have our original 2/3 n cubed, and then we have n squared for the forward substitution. We have n squared for the backward substitution, and we do that k times. So our total flop count is 2/3 n cubed plus 2n squared k. Point being that the k is multiplied by n squared, not by n cubed. Big savings for large n or large k. Big savings, large n or large k. Actually figure out how much savings you have. So that's one reason why you would do the LU decomposition. The other one we mentioned briefly when this question came up at the last lecture was computing determinants. The determinant of a lower upper triangular matrix is simply the product of the diagonal entries. And so if you want to take the determinant of A, that would be the determinant of LU, and that will be the determinant of L times the determinant of U by the properties of determinants. And because these guys are triangular, that is just the product of the entries. That is how you calculate a determinant factor and then use this fact. Okay, what we did last time was LU decomposition without pivoting. We just went through the big Gaussian elimination and we did not have to exchange rows. There's two reasons why we have to exchange rows. One is zero pivot position, and the other one is partial pivoting to control numeric stability. So in general, Gaussian elimination requires row interchanges, and that means that not all matrices can be factored exactly how we did it last time. And the other problem is that we often want to do row interchanges even when they're not necessary to control the round off error. That was the partial pivoting. So now what we're going to do is take a look at doing a factorization of our matrices when we need to do row interchanges. In order to do that, we have to introduce the idea here of a permutation matrix. And that is a matrix that you multiply onto another matrix that exchanges the rows. I think it'll be fairly obvious once I show you this example. Here's a permutation matrix. This permutation matrix is, I'm going to call it P 1, 2, y intersect, 0, 1, 0, 1, 0, 0, 0, 1. Okay. So the permutation matrix is an identity matrix that has two rows commuted. So in this case, rows 1 and 2 have been interchanged. This is the identity matrix with rows 1 or 2, 1 and 2 interchanged. So rows 1, 2 of I have been changed. Let's watch what happens when we take this nice guy P12 and we multiply by another matrix. So we take P12 and we multiply it by some 3 by 3 matrix. Okay. Go ahead do the matrix multiplication and we get this guy here. Two. The rows that you want to exchange, the matrix you're going to multiply by are exchanged in the oh yeah, right here. Okay, so now we have ways of doing all of the 3 things we can do in Gaussian elimination by multiplying by a matrix. Okay. Now what we do is we think we have this linear system, AX equals B. And we consider some permutation matrix such that if I was to multiply both the left and the right side by P, we would have a system that could be solved without the row interchanges. Right? So I've sort of collected up all of the row exchanges and put them into P. And then what we can do is factor P times A as LU. Because we basically start with going out of the way. Factor that as LU, which means that we could factor A like this. That is what's called the LU decomposition of A with infinity. Okay, got a question. Okay, you have to say one thing actually. I still want to ask some questions. I'm theoretically not supposed to put stuff if anybody has a problem, like if you're going to ask a question, you're like, I don't want me asking a question class to be on YouTube, right? Then you should not ask a question and come talk to me, right? We don't want to get ourselves, I really get myself in trouble after the fact, right? So it has to be, as an additional watch the videos here or read those an example. What we don't want to do is try to do something else and then find out about ourselves in trouble. Okay, so I still want to have discussion in the classroom, even though I am recording this. So I'm hoping that we're okay with that. I don't find it to be that big of a deal. You don't have to say, my name is blah, and my student number is this and that, right? No, right? You're just going to ask. Okay, so that being said, are there any questions right now that somebody wants to ask? In fact, my okay, now it's going to be death science. Okay. All right, so we're now in a situation where we're going to try this procedure out. And what we want is we want to find now three matrices, the permutation matrix L and U, such that we can factor like this. And you can see in this situation immediately that you have to pivot. Like even if you want wanting to do partial pivoting, you still have to do low exchange because you've got a zero in that position. So I'm going to just do the first few steps here, and then I'm going to refer you to the fact that in Canvas, I posted a 4-page detailed thing of how to do this. So here's the do this. Just okay. I don't think we're going to get a lot of value out of you doing that. 30 or 40 minutes to do. So I'm going to get us started, and then I'm going to refer you to go through that on the Canvas page. Please do it. Just print it out and go through it once, and then maybe put it to the side. See if you can do it yourself. If you can do that one and you understand what's going on, then you're done. You don't have to do any more of them except when you're asked to. Okay. All right. So we're gonna do the same thing. Proceed with Gaussian elimination, and we're gonna keep track of row interchanges. So the first thing I see that I'm gonna have to do here is I'm gonna have to make a row exchange. So I'm gonna exchange row 1, E1 with E2. And that's going to get me the row equivalent matrix that looks like this. 1, 1, minus 1, 2. 0, 0, minus 1, 1. 1, 1, 0, 3. 1, 2, minus 1. Now I'm in a position where I can do 2 row operations in order to get the zeros happening right here. Normal Gaussian elimination. So right here, I'm keeping track of this, I've made a row. Now I'm going to make those 2 things zeros. And there's 2 row operations that I need to do that. I would take E3 and subtract E1, and I'll put that back into E3. That's going to be elementary matrix E3. Then I'm going to take equation 4, that's row 4, equation 4. I'm going to subtract equation 1. And I'm going to put that back in equation 4. And that's going to be elementary matrix 4. Okay. Let's go ahead here. I have now completed the first column of the Gaussian elimination. All of these guys are 0. I am going to, in my bookkeeping scheme, keep track of the row operations in L. So L is what is going to be my lower triangular matrix. Let us just start here with the identity matrix. I'm going to erase a couple of things and put in what I already know. Okay. It's a lower triangular matrix. It is these guys that I'm going to have to figure out. Which ones can I fill in right now? I can fill in the first column. I agree with you completely. And what are the 3 numbers there that I should put in that first column? 0, 1, and 1. Why can I do that? Because I did not have an E21. This guy was already 0. I did not have an E21 elementary matrix because that guy was already 0. I have an E31 elementary matrix, and this number right here is -1. I have an E41 elementary matrix, and this number is -1. I changed the sign. That's 1 and 1. Building L as I go along. I do not know what this number is going to be. I do not know this, and I do not know this. Okay. So now I'm going to continue along with my operations, and I come to a situation where in the second pivot right here, I have a 0, and I see here I have a 1. Now I have to do another row exchange. I have to exchange row 2. I'm keeping track of these guys. Lose track of this. This is why you get super happy to have that. Okay, so I go ahead and do that. That will be then 1, 1, 1, 1, 2, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1. Here we go. These guys 0 from before. These guys, nicely 0 already. Lots of example, we don't have to do too many operations. Okay. Now I notice that those two things are 0 already. Okay, right here. What can I now do with my matrix L? Right, exactly. So this knowledge right here, don't have to do any operations. These guys are now 0. Then we have to do the row operation, make this guy 0. Okay. This is where I'm going to pause because now I'm just repeating myself. Just moving over each column, do exactly the same thing. I'm plotting through. The details of this are posted in Canva. Okay. There's steps missing here. You can see my full notes are in Canvas for this. So I proceed along, and at the end of the day, I get a Gaussian elimination ends. Gaussian elimination ends at this point of the program. I've got an upper triangular matrix. That matrix is U. Gaussian elimination is completed. Upper triangular. And at the same time, I've been building L. Tell you what that is. L. Building it as we go along. At least some people are clear about how L is being built as we move along. Okay, so now I've got an L and I've got a U. Now I have two row exchanges. I exchanged E1 E2, and I exchanged E2 E4 during this process. I kept track of those steps. That's an idea there. So that means that if I think of this as a permutation, I had one, the rows were ordered like this, and then I made a permutation, and the rows were ordered like this. I exchanged 1 and 2. And then I exchanged 2 and 4. This is now 2. And this is 4. So now I exchange 2 and 4, giving me 2, 4, 3, 1. You see what I mean? Like you that first exchange. I exchanged rows 1 and 2. They're reordered like this. Then when I exchanged rows 2 and 4, it was the second row and the fourth row that I exchanged, which was the original 1 and 4. Let us then write out what the permutation matrix is like. first row has the 1 in the 2 position. The second row has the 1 in the 4 position. The third row has the 1 in the 3 position. And the fourth row has the 1 in the first position. There. There's my permutation. All that P. Okay. No more details, actually. Now we have a situation where P can be factored. We know the 2 row changes. That's how we do it. But we don't actually have L. We don't actually have L yet. We have to adjust to find L. And then I'm going to leave those details in adjustment. So I have 2 methods of doing that. On my detailed example, I want you to look at both of those. Don't have time to go to the entire thing. But all of the details there, it is there and absolutely very detailed. So what I do want to tell you though is what MATLAB is doing. So that you use MATLAB properly. So if you want to use MATLAB to find the LU decomposition with pivoting, you go like this, L, that's the variables you want to get the answer. And it returns L, U, if L, U equals try it out. I try it out with the if you wish to try that without pivoting, you do it like this, L, U, and you will get back, you don't ask for P, you'll get back a, what it will, if I do it, let me just show you. If I do this with this matrix, I tell MATLAB to do this, you'll get this. As you can see, this is upper triangle and what else not lower triangle. Careful changes on what you're getting back out. Okay. What we're going to do, what you're going to do, is we're going to take a look on the Canvas container, and there's a file there. That file is called this LU time. So that compares last time taken for direct Gaussian elimination. So this is going to compare direct Gaussian elimination, and MATLAB does that using backslash operator. Backslash B, and that is, as we know, 2/3 and 2 steps. Then you could try doing factorized. So then what you do is you ask it to factor it. What is doing? Factor my matrix, and then solve backslash L backslash B, and you'll find that this thing is in the order of So it's a significant time saving, especially when n is large. And it is also the case that MATLAB, even the backslash command, is actually doing something for you that you may be unaware of. So for example, it's checking sometimes for certain matrix structures, in particular like binary structure, and then optimizing the algorithm based on what it's structure will look like. So you're getting already some built-in optimizations on that Gaussian elimination. Okay, we're stopping there. You guys are going to look through that example. We're going to be back with section 6.6 on the Monday. Thanks, guys.